So I've now gone over the first two sections of Chapter 11 in previous videos. These are 11.1, which was simple harmonic motion, and 11.2, which was measuring simple harmonic motion. Now I'm moving on to section 11.3, which covers the properties of waves. Wave motion results from several recognizable everyday situations. A key example is that of a rock being dropped in water. You can probably imagine the ripples that would result from this motion. In this case, water is the medium through which the waves travel. In other words, it's a physical environment where this disturbance takes place. That makes these waves mechanical. A mechanical wave is defined as a wave that requires a material medium through which to travel, so in this case, water. Now we'll take a look at some ways in which these waves can be applied. So a pulse wave is defined as a wave that consists of a single traveling movement, or pulse. So in this example, a person's hand causes this pulse within a rope that's attached to the wall, and that creates a wave that moves towards the wall. This produces simple harmonic motion, like we've discussed in the past, that can be modeled through a sine wave if we were to study this further and do calculations. Let's take a look at some types of pulse waves. The first type of wave that we're going to be studying is a transverse wave. This is a wave that vibrates perpendicularly to the direction in which it's traveling. So if we're taking this rope against the wall example, we see that the rope now has many waves in it. The direction in which it's traveling is this way, horizontally towards the wall. However, the vibrations occur in the vertical direction, in other words, perpendicular to its overall direction of movement. That's what makes the wave transverse. Here are some vocabulary words that will be useful when defining transverse waves. The first is a crest. This is the highest point above an equilibrium position. So in this example wave below, we have crests occurring here and here. Those are the highest points above its sort of neutral position in the middle. The second vocabulary term is the trough. This is the lowest point below a wave's equilibrium position. So troughs occur over here and down here. The amplitude, as I defined previously when we were discussing springs and those waves, is the maximum displacement from equilibrium position. So both crests and troughs form the amplitude, but this is just expressed as the distance away from equilibrium, which is the same in all of these cases. Finally, we have the wavelength, which is defined as the distance that the wave travels during one cycle. In this case, the wavelength would be from this peak to this one. That's one complete cycle. And that's expressed using the variable lambda, which is sort of this little swirly shape that I've drawn for you. So those are the measurements that we'll use most commonly when we're looking at transverse waves. In addition to transverse waves, we have longitudinal waves. These are waves where the particles vibrate parallel to the direction of the wave's motion. So for example, a spring or a slinky. In this case, we have a wave that's traveling in this direction across the spring, and the particles are moving back and forth in a direction that's parallel to this displacement. These waves are also modeled using sine curves, or they can be if we want to do calculations. And a real-life example of a longitudinal wave is a sound wave moving through air. Here are some terms for longitudinal waves. The first is the frequency. This is the number of waves that pass through a given point in a unit of time. So say we're looking at this sort of model wave I've drawn below. This represents coils on a spring that are stretching and then compressing. And we have a point in the middle. Now these particles are going to be constantly moving back and forth through the equilibrium point, or the point I've defined as the center. And the frequency will be described using the number of little waves that pass through the point, so basically the speed of the wave. And then the period is the time for one complete cycle of vibration. So again, these are inverse quantities. When we're looking at the motion of waves, we'll also be modeling wave speed. So we learned from previous chapters that velocity for any moving object is defined as x, or displacement, divided by the time that it takes for that displacement to occur. When we're looking at waves, however, we've learned that the displacement is really lambda, or wavelength, and the time is really the period. That would be how far it travels in a certain time. We also know that frequency is 1 over the period. So we can rewrite this as lambda times 1 over the period, or wavelength times the frequency. Therefore, we define the velocity of a wave as wavelength times frequency. That'll be useful in calculations later on. And just a note that the speed or velocity of a mechanical wave is constant for any given medium. So if you have, for example, a wave rippling through water, That wave will be constant if it stays in water. However, it would move at a different speed if it were moving through a different medium, such as air. In some cases, the motion of waves can also cause energy transfer. When energy is transferred, it is proportional to wave amplitude, or specifically the square of the amplitude of the wave. So in this case, we have energy, which I've written as E, and that's proportional to amplitude squared. So if I were to increase the amplitude, making the wave carry more energy, for instance, if I made this 2A, it would be squared, and the energy would increase by a factor of 4. Let's do some practice problems with wave properties. Number 1. A piano emits a frequency of 4200 Hz. What is the wavelength of this sound if the speed of sound in air is 340 meters per second? So I have this equation that I defined before, where velocity of a wave is equal to wavelength times frequency. Now we know that the speed of sound in air is 340 meters per second, so that'll be the velocity. Then the wavelength is what we're solving for, so we'll leave that as lambda, and then the frequency is 4200 Hz. Now if I divide both sides by 4200, I get that wavelength, or lambda, is equal to 0.08 meters, which is 8 centimeters. That's how long the wavelength is. Number 2. If the amplitude of a sound wave is increased by a factor of 4, how does the energy carried by the sound wave in a given time interval change? So we know that energy is proportional to the amplitude squared, and we're increasing the amplitude by a factor of 4. So now we have 4A on this side, and we still have energy. So if I'm squaring the 4A, I end up with 16A squared, meaning that the energy increases by a factor of 16. So you can say that the energy that's produced is 16 times as great. Number 3. A tuning fork produces a sound with a frequency of 256 Hz and a wavelength in air of 1.35 meters. What value does this give for the speed of sound in air? So now we're solving for the speed of sound, so that's v, and then once again velocity is equal to wavelength times frequency. So I'll leave this variable as v because we don't know its value yet. We know that the wavelength is 1.35 meters and the frequency is 256 Hz. If I multiply these values together, I get that the velocity of sound in air is about 345.6 meters per second, which is pretty similar to the value they gave us before of 340 meters per second.